So, hello everybody. Welcome back to the AI Agent Frontier Seminar. I'm Minjing, and today we are thrilled to have Professor Manling Lee join us from Northwestern University. Manling's research sits at a very exciting intersection of language, video, and robotics, and her work has been recognized by many awards, including the 2024 ACL Outstanding Paper Award. And for today, she will be talking about her work on RAGEN, so reinforced reasoning approaches. For many of us, this is really tackling a core challenge. How do we actually have the agent to be robust in decision making, especially over the long horizons and under the uncertain rewards? So it is incredibly relevant to our focus on safety and embodied AI. Just as usual, we will have time for Q&A towards the end. And when we get there, please use the raise a hand button and ask your questions directly. And with that, please join me in giving Professor Lee a very warm virtual welcome. Manning, the floor is yours.
Thank you. Yeah, I really appreciate the opportunity, and I'm very excited to share more about our recent thought on the agent because I think recently there are a lot of progress from different groups, and we actually see this is a very exciting stage that the agent is actually has a real impact on the daily life. And when we are trying to train agent, I think recently a lot of work is trying to identify what is still the bottleneck of the agent. And if we are doing like agent training, maybe we need to gather feedback from the environment. So we also try to share some of our thoughts on that. Basically, we want the agent to see, think, and act. I think if we try to train the agent, then we will firstly try to define like what is the ability that the agent we want to make train to have. For example, if we define the agent as doing many tasks in many environments, then basically we need agent to have two abilities. The first ability is to do goal-driven decision making so that they can achieve many tasks. And another thing is to interact with the environment, especially if there are a lot of different environment we want the model to generalize. So essentially, if we want to change from this large language model to large action model or large agent model, what we try to do is we want the agent to have these two abilities to interact with the environment and to do goal-driven decision making. So in the talk, I will basically structure this talk from two parts. The first part is about how we can understand the environment. Another part is about how we can do goal-driven decision making. The agent task is still not very well performed because when we train the large language model, we just ask the model to learn priors from our like daily conversation. For example, if we have this task set up the table, we can see the agent will actually put the turkey directly on top of the table, even the current large, most well-performing LLMs. And if we actually check this scenario by human, we definitely will not do this. We will actually use the plates. So we will actually put the turkey on top of the plates and put the plates on top of the table. So I think that basically means that for the agent training, there are a lot of word knowledge that is so fine-grained, which may not be well mentioned in our daily data in natural language. So we basically need to ask the model to interact with the word and then to understand this low-level word knowledge. So this is the trajectory we are trying to learn in the agent training work. Like we basically need to learn a trajectory of actions or a trajectory of the state changes. Then the entire process is trying to learn the agent decision making. But when we talk about decision making, the most fundamental theoretical framework is actually Markov Decision Process. So what we are trying to do is we basically just take human goal as input, and then we have two parties in the system. One part is the agent, another party is the physical world. And the input to the agent is the state, and when we ask the agent to output the actions. So a lot of cases, this agent are LLM agent or VLM agent. And then we use this action to execute this action in the physical world. So finally, we can get the reward and also the state changes after the action being executed, what is the next state. So this is how we build up this Markov decision process. It's essentially what we do to use these language models as the agents. So the first ability we just talked about is really to handle the environment. So we want the model to do state estimation because when the model is trying to observe the environment, a lot of cases, they only have the observation as input. The observation is more like partial observation. And we want the model to really understand like what is the state. So we want the model to see. This is the first step, like we want model to see before they can think and act. But we all know like currently the large language model is still not very good at spatial information, especially trying to understand the geometric. For example, this is a very simple question about like which line is longer. And as human, we definitely know like A is longer. But if we ask the language models, actually like 2 years ago when GPT-4V first came out, we identify like it always have the wrong answer. But now, even if we are using the latest GPT model, like even today, actually their answer is still like these two lines are of the equal length. So basically they mixture up this image style with some visual illusion examples. Like whenever they see this kind of two lines or asked about comparison between lenses, then the model will always recognize it's this kind of visual illusion example. So they will just answer A and B are of the same length. So they are not really trying to see the image, but trying to remember the image style. And then we try to change the image style to some other like styles, like we just change the lens into two pencils, or we can change the style into some real image. And in both cases, actually, the model can answer them correctly. So we can see this basically make us kind of doubt what actually the model is learning because we have these image caption pairs. So a lot of cases, when they are training the model is able to learn the concept, like the object concept, relationship, and actions. But they're not very good at really see the image about the geometric features. For example, previously, Sanning's paper actually categorized 9 type of the errors that the model always make. They are mainly about the orientations or color, shape, and other geometric features. Like in the first image, if we ask like where the dog is facing, a lot of cases the model will not be able to distinguish left and right. And then we can also know like there are a lot of cases the model actually perform pretty bad on this geometric structures, like their spatial relationship and the egocentricness. Like spatial relationship, basically the model is also biased towards to the prior knowledge. For example, whenever they see a cup and a table, they will always predict the cup is on top of the table, no matter the cup is below the table or on the left side or on the right side of the table. So it's basically just the trying to memorize the word frequency rather than trying to really see what is inside the image. And for the spatial relationship, there are a lot of examples, actually surprisingly bad about how these different objects are positioned. And egocentricness is more about we want the model to have embodiment in the environment. So they need to actually recognize where they are facing and what's to their left and what's to their right. And another thing is if we try to make it more challenging to have dynamics. So we want to track the state changes in the environment. Then we can see as a human, we have this mental simulation ability. Like if we place the blue chair behind a red chair or put the yellow chair behind the blue chair and then put the book on top of the chair that is in front of the blue chair. So all these kind of abilities is very simple to human, but still a lot of cases the model will make errors. And if we ask the model this kind of what if question, like if you turn right, what will behind you? The model actually also a lot of cases will mix up this kind of mental simulation or mental rotation ability. And a lot of other abilities like transition modeling and spatial reasoning in the dynamic environment and navigation, episodic memory, they're basically very challenging for the current model. As a result, when we are trying to research on this kind of ability, we try to ask the model to do more about reasoning, like when they are only seeing partial observation, like from limited views, whether we could ask the model to imagine the layout, imagine what's actually in the scenario and trying to just predict the unobservable, unseen objects. So that's what we call spatial mental modeling. If we try to build up these spatial mental models, then we basically just trying to recognize the information from different partial observations so they can connect the dots. For example, here, if we have a room and then we have 4 images from 4 different viewpoints, like left, right, front, and behind, then what we want to do as human is we want to reconstruct this space so that we can understand like the unseen objects. For example, in this question, if we only have the viewpoint 4, then given this view, if we ask the question like what's to the left of the black bag, we actually cannot recognize what's to the left because we are not able to see the scene here. As a result, what we try to do is we want to compose this spatial mental model step by step. So for example, if we have these different views, then we will check the first view, like the bag is actually in front of a door. And then we change the view, we do mental rotation, and we identify like there's a desk behind the bag in this view. And then in the third view, we can see there's a window. And in the fourth view, we can see there's a sofa. As a result, when we do mental rotation, we actually know how these different objects are located. And then we can just change our view to viewpoint 4. So we do this rotation, and then we can understand like if in viewpoint 4, to the left of the bag is actually a window. So this is how we human are trying to do to understand the scenario. But if we ask the model to do this, if we test the model on a large data set like 20,000 questions, and the model actually cannot answer them very well. So we ask the model to try different abilities like the what if dynamics we just mentioned, or we ask them to refer the object location to different objects. For example, what is the relative relationship to me, or what is the relative relationship to that chair? Or we can do perspective taking, like we can also from the sofa's perspective to check different spatial relationships between objects, and we can handle different visual patterns. And then the spatial relationship understanding ability is super bad. So we can see the latest model is even just a random performance. As a result, we feel this is a bottleneck for the current VLMs, and what we try to do is we try to teach the VLMs to approximate these spatial mental models. So the approximation actually can have 3 different formats. The first approximation is about view interpolation. We use view interpolation because we want the model to identify what is actually happening when we have these view changes. So firstly, we can see like if we change from viewpoint 1 to viewpoint 2, then we could just simulate what is the real view changes, and then we can for example, just sample the data from the real world, and then we can just input more views into the VLMs. But actually, we identify if we have more views, the model is not able to handle the visual information very, very well. So in that case, the visual information, the visual simulation actually is not the help, it's actually a noise. And then the second part, we want the model to do this free-form reasoning. So for free-form reasoning, it's more about we want the model to think step by step. For example, we just prompt the model to reason step by step. And then we can see, I'm sorry, the animation, I'm not sure what's wrong about the animation. But we can see like the free-form reasoning is actually not perform very well. And the third part is we want the model to see the cognitive map. So the cognitive map is more like we want to have a structure about what is actually the layout. So we want the model to recognize the objects and their spatial relationship. And we use a JSON format to represent that because JSON format is the most like natural format for the foundation models. And we can see if we use the cognitive map, actually their performance is around like 4% increment. And then we are thinking if we just do this kind of structures, the model is still very struggling about all the spatial mental models. So maybe we can do the training first. So for the training, as we mentioned, because we just recognize the cognitive map is very important. So the first part is we want the model to do this map, and then we can reason about it. And another baseline is about like we just do the reasoning or we just do the raw QA and we identify like this map, then reason is actually the most effective approximation that we actually need to push the model to think through this cognitive map structure, and then we can do the reasoning over this cognitive map. So the most important question about cognitive map is how well the current LLMs perform to construct cognitive map. If they can construct the cognitive map perfectly, then this problem may be already solved. So when we test these cognitive maps, the first thing we identify is like the model seems to work because it can always follow the format and it seems like generating the cognitive map very well. But then if we compare the cognitive map generated by the model with the ground truth, we calculate the overall similarity and the isomorphic rate. Actually, we can identify the isomorphic rate is pretty low. It's just maybe 15% accuracy. So we can see, although the model is seemingly to generate cognitive map, but they are only about format correctness. The real numbers within the cognitive map are actually wrong, so their similarity is really low. And then we are trying to train the model, as we mentioned, train the model to reason step by step, or use the cognitive map to train the model. So we can see, like, if we just train the model to reason step by step, the model actually is trying to push the cognitive map accuracy to around 60%. So we can see the figure B here. Like originally before training, the cognitive map accuracy, the isomorphic rate is around 15%. But now, after training, we can actually get 60% of the accuracy. So basically, the reasoning abilities improvement is highly related to the cognitive map prediction accuracy. So this is the SFT performance. And then we're trying to see whether we could try to ask the model to learn from the feedback. So we just ask the model to firstly do the SFT as we just mentioned, and then we try to do the RL training. And actually the model can achieve around like 30% improvement. So this is huge compared to the only RL-based approach or only SFT-based approach. Actually, this demonstrates the DeepSeek R1 style about trying to warm up the model using some cold start first and then ask the model to learn from feedback. It's really working well. So in this line of work, what we try to do is we want the model to reason about the environment. And then this kind of environment learning is highly dependent on whether the model has this imagination ability, the reasoning ability about what's still unseen, and then they can actually fill the gap about for the layout, whether they could just imagine the unseen objects. And then we call this like MindCube because it's mainly about asking the model to do mental simulation. After we figure out how we can make the model to better understand the state, the next thing is we want the model to do the reasoning about policy, about the action sequences. For example, if we have the state, we want the model to predict correctly about what we should execute next. So this action prediction is the most important part we want the agent model to learn. This is essentially, I think, the most LLM agent work are focusing on. And for the language agent work, we are trying to do is mainly about trying to train the large language model to do this multi-turn interaction so that they can reason about what they should execute next. And we all know this kind of reasoning, especially the RL-based approach, has been achieving great success in the past several months. Especially this RL is working with verifiable rewards. That's essentially the code task or the mathematical task. For example, these tasks, the verifiable rewards can help us to know clearly about which the LM is performing good and which part the LM is still performing wrong. But if we are changing them to the real world setting, actually it's pretty different because we are not working on single turn mathematical question anymore, but we are trying to work with the multi-turn feedback. And then for the problem, we don't just have one problem solution, but we actually have infinite state combinations. And then this final answer part, we don't just have one answer, but we actually have multiple trajectories. Maybe even if with the same goal, we can have alternative paths to achieve this goal. Another thing is we don't just try to handle one question, but we try to handle the partial observability of the environment. So we are not directly see the entire scene, but we need to understand the scenario by handling this kind of randomness and partial observability. As a result, we mainly design this algorithm to make sure they can handle this multi-turn interaction. And for the state design, we make sure the state can include these random state changes. And we also model all this state and action prediction process as a Markov decision process. So essentially, they are this kind of state action sequences. So given the initial state, we want the model to do some action and we can get the next state. And then to train this kind of state changes, if we just do the single turn training, then we could just directly update the LMs. But if we want to handle the multi-turn based training, what we are doing currently is firstly, we want the model to roll out in a multi-turn setting, and then we can leverage this multi-turn trajectory to update the LMs. So we change from training from single turn actions to directly optimize the entire multi-turn trajectory. And then we can use the PPO algorithm to do that. So the implementation is actually pretty simple. Like we just have the state, thinking, action, reward trajectory. For the current state, we ask LMs to predict the next action. So we want the model to firstly predict some thinking tokens and then predict what is the executable action. And then this executable action will be executed in the environment to get their feedback, especially about the next status. As a result, this is how we obtain these sequences of the state action sequences. And then for each trajectory, we can get their accumulated reward. And this reward will enable us to update the LMs. But one thing we care about here is that a lot of cases RL is not really working because they're not converging. So we actually need to carefully design how we should normalize this reward. So here we actually work a lot on the reward normalization. And then we can see, like, if we don't really carefully do the reward normalization, we just apply PPO and GRPO to the agent training, we can see for all these agent tasks, actually the direct application of GRPO and PPO will not lead to the success of the agent training. in a lot of cases, they will actually first increase the success rate and then drop dramatically to 0. It basically means like the model is stacking into some local minimum. For example, if we open up the model's reasoning chain, we can see when the model stack, actually, for example, we see all the model will collapse at the round 150, and all these 3 times the model actually is outputting the very same reasoning chain. This basically means like the model stack to the local minimum, like the reasoning chain is always the same, and then they will not be able to do the reasoning anymore. So this, we call it echo trap, because the model is echoing the reasoning chain. To avoid this, we actually can try to monitor these several different indicators, like the reward variance or gradient norm, or we want to monitor the output entropy. And this kind of monitor indicators can help us to quickly identify like when the model will collapse. And if we just want to improve this echo trap, we actually also think about, since we identify these indicators, maybe we could leverage this indicator to optimize the model so that they will not stuck in this echo trap. Based on the indicator we just discussed, actually it means that when the model is handling this low reward variance, like on the left side, the model will always stuck. And if it's on the right side, like if the model is handling the high reward variance, actually the model will have very good performance. As a result, we just leverage this indicator and we ask the model to not use all the trajectories. They should only select the trajectory that is high quality and be helpful to the optimization. So here what we are doing is we just filter out the trajectory based on the variance. So we only keep the 25% most high variant trajectory, so that indicate this trajectory are high quality, and then we can do the training much better. This is the work like we're trying to do about how we can stabilize the multi-turn RL training for LLM agent. And we can apply these filtering techniques and all the other RL tricks like the clipping tricks and removing the KL constraint also work pretty well for this multi-turn RL training. And we can actually also get this framework applied to other environment, because we try to make the code very well organized. And if you try to add your own environment, you can also feel free to play with our RAGEN framework. And if you have any questions, you can also feel free to let us know. The second work we try to do about this MDP policy is we not only just ask the model to act, but we ask the model to also see first and then act later. So it's kind of like combining what we just mentioned in the first section and the second section. So this is essentially the VLM agent, the multimodal agent. The difference here is that we don't just ask the model to directly see the environment, but we try to ask the model to reason about the environment, like the robot manipulation. It's highly rely on this reasoning about the object positions and what is the action we should do in the next. So for this kind of challenge, the first thing we try to handle is about we want to input the visual state, and this visual state interpretation part, we can have different format. Like we can ask the model to interpret them as a natural language, or we can use a symbolic representation, or we can use a structure like the JSON structure to represent the scenario. And then when we ask the model to do this kind of reasoning, we actually make this MDP policy to have a parallel belief space. For example, if we have this state and action sequences, what we are trying to do is like given the current state, we try to learn the transition to the next state. And for the MDP policy, the transition is more about we want to firstly observe the current state, so that is the observation stage. And given the observation stage, we will predict the action, and the action will be able to trigger the state transition. But if we have the agent, then for the agent, we actually need to have this internal belief stage. So given the current observation, we hope the agent to firstly imagine and reason about what is actually happening in this state. So that is the state belief. And then we want the model to have the action. So that is the action belief. And then we try to project this action to the real action in the scenario, and then we can execute the action. But if we want to further predict the action better, so maybe we can do the simulation about what will happen in the next. So essentially in the agent internal belief part, we will have three parts. The first part is we firstly have a belief about the current state. Like we can reason about the current scene. There's a plate on the dining table to the right. And then we can reason about the action, like what we should do after we see this state. So we want to see like maybe we firstly move forward to get closer to the table, and then move to the right to be in front of the table. And then we can simulate what will happen next in the belief space. So the belief will be more about like I will move closer to the table as the next state. So essentially, we can use this framework to a lot of tasks, not only just the like navigation task, but also the robot manipulation task. Like it's the only difference is just we change the internal belief representation. Like we can here represent the state belief more related to the JSON format, and we can use numbers to represent their positions. And then the reasoning is more about the current state, the action, and the next state. And then we can calculate the reward. So if we think about this process, then we are trying to change from the Markov decision process to the partially Markov decision process, because we need to handle this partial observability. Essentially, the previous learning is about MDP is to learn this state transition. But for the POM-DP, the partially observable environment, we actually need to include this observation. So the learning is not just about state transition, but actually also has the state estimation as observation. So we try to do the reward reasoning based on this word model. This is essentially like whether the word model will be helpful for the VLM training. The first thing about the word model is trying to interpret the current state, so that is trying to translate the observation to the state belief. And then we can see we just translate the observation, ask the model to predict the observation, and then compare the belief to the ground truth state. And then the next thing is we try to ask the model to predict the state transition. We want to know like what happens next. So we want the model to also compare their belief about next state to the ground truth next state. And the comparison can be done using the LLMs judge. As a result, this is our work about the VAGEN framework. Just ask the model to see and act. And we actually have this both VAGEN and RAGEN framework publicly available and open source in the code base and also data and the environment. So if you are interested in play with the RL learning framework, you can feel free to try them. And you can also feel free to add your own environment into them. Some interesting we discovered is that for the belief part actually is highly dependent on the task. If the task is about navigation, understanding the environment, then it's more about we try to ask the model to identify this natural language-based interpretation about the scenario. But if the task is about robot manipulation, actually structured output will be much better. And then if we try to handle the SVG tasks, the most important thing is trying to understand the trajectory, the SVG paths. So we just talked about how we can learn about the MDP policy. The next thing we can learn is about the reward model. So I will not spend much time on the reward model, but basically we have one work that we want to construct the reward from the human description like here, and then we try to construct the code structure to interpret the human feedback so they can serve as a reward function to the LM agent for robot manipulation task. This is also very interesting about how we can convert the reward so that they can actually make the model really understand what is still lagging behind for the current model, and they need to improve spatially about that. And then for the next part is we try to actually integrate the entire agent learning framework into the agent interface. So we want to connect the LMs with the environment based on the interface that is very standard for the different environment. And then for the standardization, we actually also based on the MDP policy, MDP process. So we will firstly care about the input, like the input will have the goal, and then we just ask the model to focus on this goal interpretation ability. And the second and third ability are mainly about the output part. Like we want the model to output the action sequences, and we want the model to output the state changes, that is basically subgoal decomposition. And then we also want the agent to have the ability to learn about the single step transition. So that is the transition modeling step. Essentially, we try to have these 4 different components to learn as the agent interface so that they can connect to any environment. So you can also feel free to play with this framework. In summary, what we try to do here is we try to make the large language model to have the ability to interact with the environment and to do the goal-driven decision making so that we can make them to be as the agent model to interact with the environment. And then for the environment interaction part, we want the model to have the ability to understand the color shape, this kind of geometric features, and also the geometric structures and the law of physics when we have the state changes in the environment. So we try to go to the lower level, and we also try to go to the longer horizon to make sure the model can do the reasoning much better. And essentially, we try to make sure the current foundation model is able to go back to the Markov decision process to really learn about this multi-step decision making and know about how to do the state estimation, how to do the MDP policy, and how to learn the reward model much better. So another thing we want to highlight is actually for all the work about using foundation model for embodied agents, we try to categorize this work under this MDP policy. Like for the different work, if we just categorize them based on the difference of state estimation and action sequencing and also reward modeling, so we can see like they just have different variants about how they design these embodied agents using foundation models. And then we can clearly learn the design space, and then we can do better about the foundation models for embodied agents. This also open and the public in our website. So if you are interested in check this tutorial, please feel free to check and also feel free to talk to us if you have any new thoughts or how we can better work on this direction. Another thing is for the foundation model with embodied agents part, we also have the challenge and the workshops. So in this year's Neurops, we actually have the challenge together with the behavior challenge. So we basically will offer this amount of the price, and then we are happy to see you at Neurops if you are interested in this direction. Another thing is, like we also work together with Xiaojie. He lead this development of the agent for scientific discovery and also some other data analysis work. So if you are trying to leverage agent to analyze your data, like the tables and the PDFs and other type of the data, you can feel free to try this tool. This agent is ready to use as well, so you can feel free to play with it. And we just build up our lab. I think it's actually just the maybe 1 year anniversary for me about becoming an assistant professor. So if you are interested in joining our lab, please also feel free to let us know. Thank you. I'm happy to take questions.
All right, thanks, Manling, for that great talk, and congrats on the anniversary for your first years of professorship. Yeah, the talk has really nice insights into the critical connection between embodiment and reasoning. I'm sure the folks has many questions, so let's open the floor for Q&A. So if you have any questions, feel free to raise your hand and ask directly. Yeah, so as folks are gathering their thoughts, maybe I can start with a question.
Mm-hmm,
Uh, so you have talked about the approach of multi-turn conversation and reinforcement learning,
mm-hmm,
and especially in embodiment and in problems where there is a hidden state or hidden intent, like a user's intent, or when you complete a task, some of the states may be hidden. So having the identification of this hidden state or intent would be very important for the goal completion or the alignment. So I'm wondering, in your approach of reinforcement learning, how do you encourage the agent to learn actively about, how discovering this hidden state or intent, especially when they're not explicitly stated in the problem?
mm-hmm. Yeah, so I think that's very interesting question. I actually don't have slides here, but we are working on a project called like intent kind of agent or trying to just do the intent interpretation for agent. Actually, I think that problem is very, very popular in the industry. So I also work with Amazon as an Amazon scholar, and I think that's a major topic they want me to work on for the intent prediction. Previously, we think of the intent prediction more like the classification or just the prediction problem. We want the model to maybe also verbalize their intent. But then I think goal interpretation is more about sometimes the user is also not very clear about what they want to achieve. So sometimes they actually just input a very simple sentence to the LMs, and then they hope LMs to give them some feedback, and then they adjust their input or just like continue interact with LM to figure out like what they really want to see. So here I think it's more like the goal interpretation is not some prediction problem. It's more like we want the model to dynamically track the intention. So it's kind of like a serial mind or how we can predict the belief and the goal of the user. So I think recently there's some work about a goal benchmark. Like they just have this shopping scenario, and then they kind of use some data to recover this user intention change process. And that benchmark I checked, I think it's called user benchmark or something. And I checked that benchmark, but I don't really feel we can actually leverage that data set to train the agent very well, because I think we still need to actually know more about whether there's any kind of hidden belief of the human, and for that hidden belief part, we don't actually uh, get any feedback or reward data yet. So I think the learning of this part will also highly rely on how we can design the um, I think the maybe a feedback environment that we can actually train some algorithm to make the model just directly tracks the intention. Maybe the intention track can be modeled as some state transition process. So at the beginning, the users, they are not very familiar with the intention, and then they can gradually transition that part. I think we try to have some experiment show the progress about how we can predict how we can track the intention changes recently. So we want to release a benchmark about that kind of tracking. And yeah, so if I have that kind of work, I can also keep you updated.
Sounds great. Yeah, so thanks for sharing. That benchmarks sound incredibly useful, especially when it comes to intent tracking and providing the right feedback.
Yeah.
Uh, Okay, great. So we have some questions from the chat from Ahmad Altawaha. So
Mhm.
I'll read this out. Okay. How should we decide what capabilities should be encoded in the foundation model itself versus what should be learned through online adaptation in the embodied environment?
Uh-huh.
So essentially a question about the inductive bias versus
Uh-huh.
what we actually directly learn from the interactions.
Yeah, so I think one thing will be very interesting is when we are trying to learn this interaction, what we actually are trying to learn. So I think one thing very different from the LM training is that we want to encode a world model about the environment, and that world model is specific to the environment. For example, if we ask the model to train the maybe train in the environment of a kitchen, and then we want the model to do some task in the environment of a maybe bedroom, then they are about very different objects, and they basically have different interaction like action types and also the state changes types. So I think in this scenario, we basically feel the world model is very tied to the environment because the world model is mainly about the state, like what are the option objects included in the states, and what are the action space that can translate the state in the environment. So I think when we are trying to train the agent model for anything that is specific to the world model, specific to the environment itself, it should be learned from the interaction. And then for the agent training, we still want to have some common abilities. That common ability is basically, for example, the goal interpretation ability is not tied into the environment. It's more related to like how we understand users interaction. And then this kind of ability should not be trained for the in the interaction stage. I think it's more related to the like foundation model stage. And then another thing is for all the common sense knowledge, we identify like common sense knowledge should be more included in the foundation model stage. But for any kind of object or instance level knowledge, we should learn them through the maybe interaction or learn them or incorporate them as some retrieval or memory. So I think that's my understanding about this question. Yeah.
Yeah, thanks for your answer. So let's move on to ITM. I see ITN, you have your hand raised. Go ahead with your question.
Hi, Professor Lee.
Hi.
I'm working on wireless network configuration, and I'm
Uh-huh.
trying. Yeah, we are trying to use maybe like LM or IM agent to to do the wireless network optimization automatically. Because currently, if you want to deploy a network, then first you have to perform simulations.
Uh-huh.
There's like a a quality of service requirement. So you have to, based on those requirements, to find the better network configuration parameters for your network. And then when you deploy the real world, like a physical test bed, you can use those parameter choose by the simulation. The thing is, there's kind of like a simulation to reality gap. I think this question also exists in like a embodied AI. So the thing is we it's very sometimes it's very difficult to perform this training in real world in our case, because you already set up a network and it is be used by the user. It's very difficult to like tune the parameters, like change the parameters of the network, because that would have like a real-time influence. So the thing is, currently there, how we like bridge the gap is that we would collect, because we have a lot of simulators, so we can collect a lot of simulation data. But the thing is that we don't have a lot of access to like a lot of physical data, or maybe the data from the target domain. So we would use like traditional domain gap, domain adaptation methods to bridge the gap. But when it came to the agent, I mean the LM agent era, what do you think is a better way to maybe bridge this gap to build the more like the open world model?
Yeah, so I'm not quite sure whether I understand it correctly. So it's mainly about like you have existing model that has already been deployed and with real users, so it's very hard for you to actually adapt this model. So it's more about you want to kind of do domain adaptation directly, and so I'm not quite sure whether your question is mainly about how LM agents can do domain adaptation. Is that your question?
Yeah.
I
Or
see.
maybe
Uh-huh.
yeah. Or maybe are there maybe better ways to do this to bridge the gap?
Uh-huh. So I think for the LM agent, actually, at the beginning, we try to highlight the key, maybe a lot of people try to work on this vision, research vision about generalist agent that can transfer between different environment and can do tasks that are unseen. So I think for this kind of ability, we previously don't really highlight domain adaptation, but try to talk about like these vertical agents. Like we have the agents working in different scenarios, and these agents we call them like vertical in vertical agents, or just the agents in the vertical scenario. And then I think people get this idea about for the transferring between these vertical scenarios, the domain adaptation you mentioned, it's not kind of I think it's not just the directly transferable. It's more about we should transfer from several stages. For example, I think a lot of people are working on AI for science. That's a totally different domain, and the current language model is not able to do that. So the foundation model training part, they actually try to firstly leverage the existing foundation model, but just to do the post training on a lot of scientific documents, or just ask the model to maybe introduce another kind of encoder to encode their molecular structure. So I think for the pre-training part, most of the cases, people will still leverage language as a bridge. It's just adding some more encoder to align to the language space. And then this pre-training stage, I think is more like a cold start or warm up for the domain adaptation. And maybe a lot of domain adaptation algorithm actually are applied to this foundation model post-training stage or pre-training stage. And then later, I think for the agent part, I actually feel like agent is highly related to the environment. So if the essential like world model, I mean, what are the actions involved are changed, then we basically need the model to adapt to a new environment. So for that part, I think most people are doing this kind of RL-based training. I'm not sure like how people actually leverage domain adaptation in this field, because yeah, I think most of the paper I read about domain adaptation is still more about the foundation model part. And for the agent part, I think something I kind of feel will be useful is a tool learning based approach. So if you just train the agent more like generalized agent to leverage different tools, when you adapt to a new domain, then the model should still have ability to call the new tools. So that's how they can actually more seamlessly adapt to a new scenario. Do you think that answers your question?
Yes, yes. But also, I think what do you think of maybe like a self-evolving agent? Like, for the agent to learn itself. I think for my research, I think the submission the environment did change because for the submission and the target, the environment changes. The
I see.
things it's very difficult to perform experiment directly on the physical test bed. So if the agent can evolve, yeah, can evolve automatically, and then it will be better.
Yeah. So I think for that part, like people are using reinforcement learning just to collect the feedback. I previously worked with a company that they try to do some A/B test. I'm not sure whether it's doable in your environment, but basically, when they update the environment, they only update that partially to some specific users, and then they can get the feedback. So their update can always like do it iteratively for different user group, and people don't really feel much about that.
Cool. Nice. Okay, thank you.
Thank you.
Okay, thanks for the question and the discussion. Okay, I see a hand raised and there is a chat. So let's actually have the chat first, and then we'll go to Ingan, keeping track of time. And the question actually is also relevant to our discussion because one way to look at domain adaptation is to treat it as a POM-DP problem. And you also mentioned about your methods using the internal belief stage during the POM-DP. So the question is, how do you simulate that stage, and wouldn't it lead to a higher latency when we work in a real-time environment?
Yeah, so I think when we do the training, actually it's still this region-based framework that we will have two stage. We will have the rollout stage and we will have the training stage. So for the rollout stage, when we do this POM-DP based rollout, it's kind of like this. Like we will ask the model to save all the observation, state, and action, and also the belief or state belief action. So we can see like for the rollout stage, actually all the state will be saved directly. So the state is kind of like in this scenario, they are directly obtained from the simulator. So we basically know the ground truth their position coordinates of each object, and then for the belief stage, they are the for the belief space, they are just the output from LLMs. So we can actually save them during the rollout stage, and when we are doing the updating stage later. So the updating stage is still very similar to this one. Like we just get all the rollout. So it's kind of like we after the rollout stage, all the trajectories, they are just the data saved already, and then we just do the update here using all the rollout trajectory, and then this part will not suffer from any latency or delay. So I think the rollout stage, the trajectory generation stage, is actually time consuming.
Yeah, thanks for that answer. And yeah, lastly, let's go to Ingan. Ingan Wang, see your hand raised. Please go ahead.
Oh yeah, thank you. So I want to ask about the reward variance that you mentioned in the presentation. So what could you like dive into it more? Like, would it penalize if it's partially correct reasoning, or like when the model hallucinates? Like, I'm curious like how that affects the multi-turn task here.
So here, I think for the quality-wise, we basically just, as we mentioned, like when we have this two stage, the model will firstly generate all the trajectory. And for all this trajectory generation, we do identify like when the model is doing multi-turn, the reasoning chain will become shorter and shorter, and that is not a good thing. So when we do this kind of data selection, like high quality data basically means the reasoning chain should be long and the reasoning chain should be diverse between each different turn. So if the reasoning chain is like they always kind of repeat their reasoning, then it's not a good reasoning chain. So I think for the variance, for the entropy-based ranking of the trajectory, it's more about we want to select the trajectory that are long and also diverse between each turn. So this is a ranking about all the trajectory. And for the hallucination part, I don't think here, like when we do the trajectory selection, we can actually handle a hallucination problem. But I think generally hallucination is more about if we want the model to output action, and if that action is not executable, then the action will already be filtered out in this raw stage. So if the action is not being able to execute in the environment, they will directly not include in the trajectory. So all the trajectory generated, they are actually like executable action. And also all this trajectory will be able to achieve the goal. So that is kind of how we collect the trajectories. So I think for the hallucination part, they're more about when we are generating the trajectory, like how we can actually only keep the trajectory that are kind of a valid trajectory. Yeah. Another thing related to hallucination is maybe like when we are working on the VAGEN framework, we actually have this additional comparison about the state. So they predict the current state and next state, and then we compare with the ground truth state. And for this part, we actually leverage LLM as a judge. So that is also helpful about hallucination. Like during training, the model will need to learn to predict the state that is most closely related to the ground truth state, so they will not kind of hallucinate, learn to not hallucinate.
Okay, great. And
Thank
on
you.
that note, yes, thank you. Let's give our speaker another round of virtual applause for sharing her insights. And thank you all for your engagement. That's pretty much it for today's seminar. We look forward to seeing you all next week, and have a great weekend, everybody.
Thank you. Really appreciate the sharing. And if you have any questions, you can feel free to reach out later. Or if you want to collaborate more, we are happy to talk. Thank you.
Bye.
All right, thank you. Bye.
Thank you.